Lecture number 7, Compounds, Introduction to Bonding and Nomenclature, Part 1. So let's go back, now we've talked about matter and pure substance versus mixture, elements and compounds. Now we're going to start taking those elements, those atoms that we've talked about up till now, and building them together to make compounds. So today we're going to spend a large time today and then again on Thursday, spend a large amount of time talking about these compounds. And the compounds can be formed by looking at the way they bond, or those atoms themselves interact. It can be one of two ways, either ionic or covalent. And we'll talk about what each of those means in a second. But the simplest way to recognize which is ionic compounds always come between a metal and a nonmetal, or a metal and a group of nonmetals. Where covalent compounds occur where we have nonmetal-nonmetal interactions, or nonmetal-metalloid interactions. So if they're very on that nonmetal side of the periodic table, they're going to form covalent compounds. If they're a metal very far apart on the periodic table, they're going to form these ionic compounds. So let's start talking a little bit more in detail about these covalent compounds. They're going to form a covalent bond, which is sharing of electrons. So if we look at these two atoms that are far apart, they have no interaction. As they come closer together, now the electrons of one atom are going to be attracted to the protons of the other. And at the same time, the protons of one atom will be attracted to the electrons in the other, until they get a point where they get close enough that this interaction, this attraction between the protons and the electrons is going to overcome any repulsion that they have. So they're going to share these electrons, and because of this intra-attraction. Right? We see this strongly in some of the actual compounds or elements themselves. Things on the periodic table like nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They naturally come together to form this, what we call diatomic molecule, where there's nitrogen exists as N2, oxygen exists as 2 oxygens, and so on. Then some of the other naturally occurring compounds of these elements, like phosphorus, will exist as a tetratomic molecule, where it's P4. Sulfur is an octoatomic molecule, where there's S8 as its elemental form. So these molecules, the sharing of electrons is particularly stable in these nonmetals, and their elemental states reflect that. So let's then talk about naming these molecules. So when we talk about these covalent nonmetal bonding compounds, we're going to call those molecular compounds. And we always name them with the element that's furthest from the left or closest to the bottom is listed first. If there's more than one of those atoms present, then we have to use the prefix indicated here in the table to indicate how many there are. So if there's one, we would use mono. Sometimes we ignore that. 2 di, 3 tri, 4 tetra, and so on. So that we're indicating not only what elements are present, but how many of them there are in this compound. And then the second element, or the last element in this name, which would be the furthest to the right or the furthest up, is going to be, we're going to change its ending to "ide." Okay, so we'll go through some examples in a second. But we have to be aware of some common names like water, ammonia, methane. C60 is commonly referred to as Buckminster fullerene. So there are some common names to these molecular compounds, but systematically let's talk about how to name those. So if we look at these three examples, the first one, BF3, the furthest to the left or the furthest down is phosphorus, so it's going to be listed first. So we call there's one of them, so it would be phosphorus. And then we have 3 fluorines present, so this would be trifluoride. We change fluorine, we change the ending to "ide", so phosphorus trifluoride. Another example is boron trichloride. So there's 1 boron, 3 chlorines. So let's go the other way now and look at this next example, tetraphosphorus decasulfide. So we have phosphorus again, but the prefix tetra tells us there's 4 of them, so it's P4. And then sulfide, change the ending from "ide", gives us sulfur, and the deca tells us there's 10. So the formula for this molecular compound is P4S10. So we should be able to move back and forth between these names. Fairly simple naming convention. Furthest to the left, furthest down, it's listed first, or if there's only one of them, the one that has more or is furthest up and furthest to the right, is going to be the one that we change the ending to "-ide." Again, in both cases, we indicate how many there are with the appropriate prefix. Okay. So these covalent compounds are the sort of the easiest to name and sort of recognize. We'll spend a whole bunch of time talking about what they look like three-dimensionally later, but let's now switch back and talk about these ionic compounds. If covalent is sharing electrons, ionic is a complete transfer. So one atom is transferring electrons to another. And when this occurs, we actually get what we call ions, some charged species. And the compound itself is being formed from the attraction between these positive and negatively charged, following Coulomb's law, which says that the energy of attraction between particles is directly proportional to the product of the charges and inversely proportional to the distance between them. So the larger the charge, the more they're going to attract. The further apart they are, the less they're going to attract. So they're inversely proportional. So if we look at on the side here, we see that if we take sodium metal and chlorine gas, sodium metal being in the gray and chlorine gas being in those green compound or molecules. If we bring them together, if we look at an atomic view, sodium typically has 11 protons and 11 electrons. Chlorine, each atom has 17 protons, 17 electrons. When they come together in close proximity, that sodium is actually going to transfer one of its electrons to the chlorine to give it now 10 electrons for the sodium, and chlorine is then going to have 18 electrons. So we get now two charged species. Right? And then it's the attraction between that positively charged and the negatively charged that's going to allow us to form this sodium chloride crystal. And we see that the interaction is going to make that total charge 0. So in all cases, all of these ionic compounds, the total charge that's going to exist is 0. So we're going to manipulate the charges and the number of atoms based on charge to get this total charge of 0. So if we go back to this definition of an ion, it's a charged atom or group of atoms that has a net positive or negative charge. So if it's positively charged, we're going to call that a cation. And that results from the loss of one or more electrons. So for sodium, we said we had 11 protons, 11 electrons in the neutral. We're now going to go to a sodium plus 1 where we have 11 protons and 10 electrons. For the anion, which is the opposite of negatively charged ion, we're going to gain one or more electrons. So chlorine, 17 electrons, we're going to gain 1 to 18 electrons. And we'll see that there's a corresponding change inside, which we'll discuss next semester probably. So we're going to see that this always is the case. We can predict, so these ions can exist in a variety of different things. We have a monoatomic ion, which is always one ion, so chlorine, sodium, calcium, oxygen, aluminum, all of these are examples of a single monoatomic ion, one element, an ion. We can also have some polyatomic ions, which contains more than one atom connected in some sort of covalent arrangement, but the overall has a negative or positive charge. We'll spend quite a bit of time in the next lecture talking about these polyatomics and some of the rules we have for naming them. Now we're going to talk about more simpler cases. So when we form these ionic compounds, it's the anion and the cation to come together. We can predict for some atoms or elements what their charge is going to be when they form ions based on where they are on the periodic table. So we see the alkali metals always form a +1 ion, a +1 cation. And the alkali earth metals form a +2. Everything in between typically has a variable number of ions. It can form multiple different ions. So in the transition metals and even into the sort of the metalloid region, we don't have a specific single ion. Where we look at the oxygen group, those typically form a -2, and the halogens typically form a -1 ion. So based on its place on the location, we sometimes can determine its charge. So you need to memorize alkali metals always +1, alkali earth always +2, halogens always -1. So then when we come together, we're going to balance these charges so that the total, the sum of the anions and the cations, has a total charge of 0. So if we take aluminum 3 plus ion and the oxygen 2 minus ion and bring them together, those charges has to cancel out. We're going to use that using the least common multiple, which is 6. So we have to bring a total of 6 plus charges and a total of 6 minus charges. So in order to get that, we're going to take 2 aluminums, each being plus 3, gives us a total of plus 6, and 3 oxygens. Each of those oxygens, again, minus 2, so that gives us a minus 6. So when they form this ionic compound, we're going to get Al2O3 with a total charge of 0. We can do the same thing for calcium and 2 plus and bromine minus, excuse me, calcium 2 plus, bromine minus. Now our least common multiple is going to be 2, so if we have one of those calcium 2 pluses, it's going to be canceled out by 2 of these bromine 1 minuses. So we get a molecular formula of CaBr2. So then if we know the 2 ions, we can come together and make the compound. Likewise, if we have just the compound formula, we can then break those 2 apart into their individual ions. For example, if we look at Na2CO3, Na, remember, it's an alkali metal, so it typically has a plus 1 charge, indicated the same here. So there's 2 of those present, so we have a total of plus 2 charge, which means that the anion has to be a negative 2 charge. There's only one of the CO3s present. So that means that the 2 ions themselves, the cation is the Na plus, the anion is the CO3 2 minus. So we can work either direction from these ions to form the compounds, or take the compounds and break them apart into ions. So when we name these, we're not going to worry so much about how many elements there are of each type, because those are going to be dictated by the charge, but are going to be concerned with the individual elements themselves. So we always list the cation first, followed by the anion. The cation we name just as the element's name. The anion, we change the ending of that element name to "-ide". So for example, NaCl, the cation, the first one listed is sodium, excuse me. First one listed is sodium. So we name it sodium. The second one, the anion, is the chlorine. Change the ending to "-ide", so make chloride. So this NaCl is sodium chloride. We see the same thing with BaBr2. Cation is barium. The anion is bromine. Change the ending to "-ide", so BaBr2 is barium bromide. And same thing for the last one, K2O is potassium oxide. So the anions, always change the ending to "-ide", cations first, anions second. For those elements that have the potential to have more than one charge, we have to indicate which charge is present in that compound here in parentheses with Roman numerals. So for example, FeCl, iron, in this case we saw on the figure earlier, can have more than one charge. So the one present here we have to calculate from what it is. So chlorine is a halogen. Halogens have a -1 charge. So there's 2 chlorines, so that gives a total negative of -2, which has to be balanced by that 1 iron, so it has to have a +2 charge. So we would name this compound iron 2 chloride. If there's 3 chlorines present, like in the next example, we would call that iron 3 chloride. Again, indicating the charge on that transition metal in parentheses. Last one's a little bit more complicated, Cr2S3. Sulfur is right below oxygen, has a -2 charge. There are 3 of them, so we have a total negative of -6, which must be canceled out by the positive charge present. In this case, we have 2 of them, so we take 6 divided by 2, gives us 3, so the chromium has to have a charge of 3+, so it would be chromium 3 sulfide. Okay. Transition metals, those that have multiple charges, we have to indicate that charge in parentheses as a Roman numeral.